Hello everyone. In this video I'm going to be going over the unit circle. And what the unit circle is what the hell is going on up here? Gonna start over now. What the fuck is going on? Hello everyone. In today's video I'm going to be going over the unit circle. And what the unit circle is it's a way that we can generalize the trigonometric functions that we've been working with so far to allow them to take a wider variety of inputs, and it will also help conceptualize them in a way that relates them to the graph on the Cartesian plane. And I know that's a lot of information to take in at once, but perhaps you'd understand it better if I were to just draw it out. So let's just say we have a normal right triangle. And here's one of our interior angles, theta. So as long as this theta is between 0 and 90 degrees, everything is well and good. But what if this angle were to exceed 90 degrees? Or perhaps even be negative? How would we conceptualize that? We can't represent that in terms of at least visually in terms of our standard right triangle. So we have to look for a way to expand the definition so that our trigonometric ratios can take in these values. And the way that we do that is the unit circle. So allow me to demonstrate what the unit circle is. To start, I'm just going to draw a standard XY Cartesian plane. And now I want you to consider a circle along this plane with its center at the origin and radius 1. And now what we can do with this circle is we can draw a line from the center to anywhere on the circumference. And then we can draw another line down to the x-axis. And that's going to form the right angle of a right triangle. And this works for every quadrant. You can go ahead and pause the video and try that out if you like. Or you can just take my word on it, which I highly recommend you don't. Mathematics is all about rigidity. But you may be wondering, okay, so you've defined the triangle in this way, so what comes of that? Well, it turns out, when you look at it this way, a few interesting properties arise about particularly the sine and cosine functions. So if you have your radius equal to 1, and let me just get the sides of this triangle straight real quick. So if this is sort of the arc of the angle we're looking at, then this is going to be our angle theta, defined with reference to the circle. I would label that, but it's probably a bit small. Actually, never mind. There we go. So, what would happen if I were to take the sine of theta, for instance? Sine of theta. Well, we don't know what the opposite side is, but we do know that the opposite side is entirely vertical. And thus, the opposite side represents the y-coordinate of wherever our radius ends up. So I'm just going to label that. I'm going to label this ordered pair first as x, y. And this is wherever our radius sort of vector meets the circumference. And so we know that the opposite side represents the vertical component of this point, or the y component. And thus, it is the y value of this coordinate. And the radius, well, we've defined it to just be 1. So the sine of the angle along the unit circle is just equal to the y coordinate. And similarly, if we try this with cosine of theta, well, cosine is adjacent over hypotenuse. And the adjacent side is going to be the horizontal component of this right triangle. Or, with reference to the plane here, it's going to be the x-coordinate. And since it's adjacent over hypotenuse, the hypotenuse is still just 1. So, we have cosine of theta is just equal to the x-coordinate of this point along the unit circle. And finally, tangent of theta, our other trigonometric ratio. Well, what's tangent? Tangent is opposite side over adjacent side. And since we already know that opposite side is y and adjacent side is x, then that means that tangent of theta is equal to the y coordinate over the x coordinate. But since we know that y is equal to sine and x is equal to cosine, this also means that the tangent of theta is also equal to the sine of theta over the cosine of theta. So there's some nice little identities that we've got from our unit circle definition, but we can go further with this by applying the Pythagorean theorem. So, the Pythagorean theorem, a squared plus b squared equals c squared. Well, what are our a and b in this cases? Those are going to be these two sides of our right triangle. So our x and our y, or in other words, our sine and our cosine. So if we plug that in, we get sine squared theta plus cosine squared theta equals, well, c squared, that's going to be the hypotenuse squared. And we know that the hypotenuse is 1, just based on how we defined our circle. So that's going to be 1 squared, or just 1. And this is probably one of the most important identities that you'll ever see in trigonometry. And it's certainly going to come in handy in the videos, the upcoming videos on the law of sines and the law of cosines. But you may be saying, this is all well and good, but we haven't answered our original question. How do we define angles, that are sort of beyond this first quadrant, that are perhaps more than 90 degrees or less than 0 degrees? Well, this is where we have to keep this definition of our trigonometric ratios in mind, our sine being the y-coordinate and our cosine being the x-coordinate. So let's say I wanted to define an angle in the second quadrant. So I'm just going to choose an arbitrary angle, and I'll label it in red. Let's say this angle is 7 pi over 6 radians. And I'm going to try and mark this out as best I can. And I'm going to label it theta sub 1, so we don't get it mixed up with this one. And, well, as we've defined our unit circle earlier, or as we've defined our right triangle within the unit circle, it's constructed by drawing this line from the point along the circumference down to the x-axis. And that's going to form a right angle. Actually, hold on a minute. I just realized after recording for about 5 minutes that this angle is not going to work for this quadrant because it is greater than pi radians. So we're going to choose something else real quick. Sticking with the pi over 6 trend, for no other reason than why not. Let's go with 5 pi over 6. And that's going to be our theta sub 1. And what you'll notice here is that if we are to actually construct our right triangle with respect to the x-axis, and this is our internal angle that we're looking at here, I'm going to call this theta sub 2. Sorry if that's a bit hard to read, I'm not really working with a lot of space here. You'll notice that theta sub 1 and theta sub 2 are going to add up to pi radians because they're making a full half turn here. So you could say that theta sub 2, the angle that we're looking for, is equal to pi radians minus theta sub 1. And this is true for any angle that lands in the second quadrant. This is the formula that you're going to use to find the equivalent angle to initially solve for the values of the right triangle. And I'm going to show you what I mean by that by working through this example of 5 pi over 6. So what is our theta sub 2 in this case? Well, 5 pi over 6, pi minus 5 pi over 6, well, that's just equal to, I need to make sure I use the right color here. That's a terrible theta, but we're going to roll with it. That's just going to be pi over 6. And from our special triangles video, we know how to solve for the ratios of this angle. So let's just draw that triangle out real quick. So this is going to be our 30, 60, 90 triangle. But I'm going to define everything in terms of radians because that's the metric that is more commonly used in mathematics, the ones that you're going to see on your tests. And if you'll remember back to our special triangles video, these ratios are going to be 1 to root 3 to 2, if you'll remember back to the special triangles video. And so now, for instance, let's take the cosine of our theta sub 2. So the cosine of theta sub 2, cosine is adjacent over hypotenuse, so that's going to be root 3 over 2. And this looks all well and good, but if you remember this definition where they're equal to the x-coordinates, or the cosine is equal to the x-coordinate, the sine is equal to the y-coordinate, since our x-coordinate for this angle is in the negative domain, we have to be conscious of that. So that means we're going to put a negative on our result. And that's the thing about the unit circle. That's how we're able to compensate for and imagine these angles greater than 90 degrees. It's in terms of this dimensionality and this negative. So if you're to go over the 90-degree limit that was previously imposed on our trigonometric functions, though no more, all you have to do is consider the sign. And it's going to vary between each function and each quadrant that you're going into. But this is how we conceptualize these angles. And I think that's really elegant, personally. But back to the actual math. So that's how we would do this for 5 pi over 6. We just find the equivalent angle, our theta sub 2. We solve for that, and then we consider the dimensionality. And that's really all you have to do for problems like this. But for the sake of thoroughness, I'm going to go through and show you all the formulas to find equivalent angles for each of the quadrants. If you think you've got a handle on this, you can go ahead and pause the video and try and derive that yourself. But I'm going to go through this anyways, just for the sake of clarity, to make sure everyone's on the same page. So, what if you're going all the way into the third quadrant? Here's our new vector and our angle. Sorry, this is getting a little bit messy here, but it's going to look something like this. Let me just choose an arbitrary angle that would be in the third quadrant to help conceptualize this. Let's say, I'm thinking 5 pi over 4. So, how would we bring this to an equivalent angle? Well, first of all, let's draw our equivalent right angle. So, again, it's with reference to the x-axis. And there it is. There's our right angle. So, you'll notice that this right triangle here, it becomes equal to this angle minus pi radians, because this sort of half circle here is getting cut off by this side, by the x-axis, which becomes a side in this right triangle. So the formula for the third quadrant becomes, so an angle in the third quadrant is equivalent to theta sub, I forget what I'm defining this with reference to, I'm sorry guys, theta sub 3 is equal to let's call this angle theta sub 3 sub 1, and this is going to be our equivalent angle. Sorry if that's confusing, but this is entirely my fault. I should have rehearsed this video more, and I'm getting all weird with my notation. But if you have any questions, please leave them in the comments. Again, I make these videos for you guys to help you all out with your math, and so if I'm not explaining things clearly, then I ain't doing my job. So make sure if you got any questions, put them below. But back to the math. Our theta sub 3 sub 1, our equivalent angle, is equal to our original angle minus pi radians. Because we're sort of hacking this half circle off so we can have a complete right triangle here. And now finally, what about an angle in the fourth quadrant? If we're to go all the way around. And this is sort of your arc here. Well, what does our right triangle become? If we define it with reference to the x-axis, well, there we have it. There's our right triangle. I'm going to call this our new equivalent angle, sort of following in the spirit of our last one. I'm going to call this angle becomes theta sub 4 sub 1, since it's being represented in the fourth quadrant. And this is going to be equal to, so we know just from the definition of our radians that 2 pi radians is equal to a full revolution. And so, since we're on the last quadrant, and we're closing in on that 2 radians, this angle, our theta sub 4 sub 1, is simply what is cut out of that full circle, if that makes any sense. So therefore, that's going to be equal to 2 pi minus theta sub 4. And there you have it. That's how you get your equivalent angles for every conceivable quadrant on the unit circle. But now I'd like to consider the case of a negative angle, because as it is now we've just been considering positive angles. And if you'll notice, I've been going in the counterclockwise direction to represent positive angles. And so therefore, to represent negative angles, we're going to go in the clockwise direction. And I'm going to start a new page here to demonstrate that. So I'm just going to draw out our unit circle again along our same xy plane. So there we have it. There's y, there's x. So what if I wanted to go in a negative direction? And let's say the first of these negative angles landed me in the fourth quadrant. So let's call this negative theta 1. So this one, when it lands in the fourth quadrant, well, it constructs a right triangle pretty easy. So its equivalent angle is just itself, because you don't have to do any workarounds to get a proper right triangle. Well, what about if it landed in the second quadrant? Let's call this angle theta sub 2. Let's say this is a negative angle that lands in the third quadrant. So in a similar manner to the positive angles, this is just equal to our pi radians are 180 degrees minus this little bit that we're considering for our right triangle, or our equivalent angle. And so in the spirit of the notation that I've been using so far, we're going to call our equivalent angle theta sub 2 sub 1. And it's equal to a full 180 minus whatever we use to get to the right triangle. So that's going to be pi. And actually, since this is negative, there's going to be a sign change here. So this is going to be pi plus theta sub 2, since we know this is negative. And moving on to the third quadrant, or the second quadrant in the negative case. There's our angle, just an arbitrary angle, and there's our right triangle that we can form as a result of that. It's a horrible looking right triangle, but it works, so whatever. And there's the arc that we sort of used to get there. There's our theta sub 3, our third angle here. And so you'll notice that this equivalent angle is just our And so you'll notice that our equivalent angle here is just equal to our theta sub 3 minus our pi radians, since we just sort of have to hack this half circle off to get a proper right triangle. And so, therefore, theta, I'm using the wrong colors here. I don't know why I'm just using black for these equivalent angles. I really should be color coding them, but mathematics is not a very colorful discipline. I don't know. I'm just lazy, point being. And so this is going to be equal to our theta sub 3 minus pi. And finally, what about a rotation that lands us in the first quadrant? There's our right triangle. There's our arc. Well, similar to the manner in which a near full rotation would be handled in the positive direction, this is just going to be equal to whatever this angle is. Or sorry, it's going to be equal to 2 pi of full rotation minus whatever this angle is. And that's going to give us this sort of pie slice of a right triangle right here. So, theta sub 4 sub 1, that's going to be this equivalent angle right here, is equal to 2 pi plus, since our angle is negative, remember, theta sub 4. And I should label this on the graph here. Theta sub 4 is this orange looking thing. And, there you have it. That's how you find your equivalent angles from which you can do the trig functions for any negative input, as well as we discussed before, any input over 90 degrees. And that's what makes this unit circle so powerful. Oh, hold on. Forgive me, I made a mistake here. This should be theta sub 3 plus pi, since this is negative. You'll notice that the signs just sort of reverse since we're going in the negative direction, which makes sense because negative is just reversed positive. Clockwise is just reversed counterclockwise. It's all dimensionality. That's all it is. But anyways, that's what makes the unit circle such a powerful tool. Is it allows us to expand the definition of our sine, cosine, and tangent functions, as well as the cofunctions. And we get from a very restricted domain of theta being between 0 and pi over 2 radians, and by the unit circle, theta can be any number that we want it to be. Or if we wanted to express this a bit more mathematical, in more mathematical terms, we might say that theta is now an element of all the real numbers. So you can take any number you could possibly conceive of, plug it into theta, and you'll get a result for your trig ratio. And I'm just going to leave it at reals for now because complex, that just adds a whole new layer of complication to it. But I'm hoping you're already starting to see what a powerful tool this unit circle will be. And in the next video, we're going to be putting it to use by giving a few examples and some applications of this very wonderful thing. And I know this was a bit longer video. I appreciate your patience staying with me through all the jump cuts. This video was a bit tedious to make, and I did leave out some information, so I had to edit it all together. But hopefully the final product is informative and will help you in your future endeavors. But anyways, I'm going to sign off for now. Hope you all have a great day.